Welcome back. So in this video we are going to go over the part B of the challenge 3 multi-node broadcast. So let's see what this challenge is about. So in this challenge we will build on our single node broadcast implementation that we did in the previous video, and the main task is to replicate our messages across a cluster that has no network partitions. So meaning of having no network partitions is that we can perform inter node communication without worrying that those messages will be delivered or not. So whenever there is a network partition, there is no guarantee that inter node communications will be communicated assuredly. So in this challenge that is not the case, so we can send as many inter node messages as we want. So in the challenge, your node should propagate values it sees from broadcast messages to the other nodes in the cluster. It can use the topology passed to your node in the topology message, or you can build your own topology. The goal is to make sure that a message that is passed through the broadcast RPC message to all the nodes in the cluster. Doesn't matter what topology you use or what sort of communication that you use. The simplest approach is to simply send the node's entire data set on every message. However, that is not practical in a real world system. Instead, try to send data more efficiently as if you are building a real broadcast system. So in this, I will just go through a working solution. It may not be the best. I just found out whatever was best according to me, and because there are later parts to this challenge, which will test our accuracy and performance as well. So I'm just going to present a working solution for this challenge. So in this challenge we need to run our binary against this command, and in this time we have 5 nodes in our cluster, and this will run the test for 20 seconds at the rate of 10 messages per second. Okay, so let's go through some diagram to understand what is expected from our solution. So this is the layout of our multi-node broadcast. So if you see, we have 5 servers, 5 nodes in our cluster. This green set is the cluster and it contains 5 nodes, and there are multiple clients which are going to communicate with any of the nodes in this cluster. So as you can see, this red marks or red lines are for the client server communication, and blue ones are for inter-cluster communications, which is possible in this challenge. So the format that client server communication is going to follow is the same as that we saw in the previous challenge, and for intercommunication we introduce a new format where the message type is same, but we just need to send different values in our body. So let's also take an example where we see how inter-process communication is helpful. So let's say client A makes a broadcast message to this node asking it to broadcast a message with value 10, and this client makes the broadcast message with value 20 to the other node. So right now they don't have information about each other. They just know that their own value. So n1 contains the message 10, n2 contains the message 20. But we don't need to assure the clients that immediately after you send a message it will come to the same state immediately. We can provide eventual consistency, saying that immediately it is not being processed to the same state, but in some time, let's say 1-2 seconds, or maybe in the future it will eventually become consistent. And to make them consistent, we are going to introduce this two communications between these two nodes. So let's say the node n1 sends a message to node n2 with this format. So if you send that if you send a message from n1 to n2, source is n1, destination is n2, with this body, we are saying that this is an internal message, not someone that you received from the client. And we are saying that I received a new message 10, so just add 10 in your messages list. Similarly, n2 will send a message to n1 saying that I received a new message 20, so you also add 20 in your list. So eventually what will happen, once these two messages are passed, these two nodes will come to this same state, that is 10 and 20 in both of them. So this is the basic idea of performing internode communication, which is the same as the gossip protocol, as you can see. And there are multiple easy or even efficient solutions to this, but we are just going to follow this thing. Whenever a broadcast message comes, we are going to so suppose a broadcast message comes to a certain node, it is going to send an internal message to all the other nodes in the cluster. It is going to send this message. So in this case I have taken the example that there are only two nodes in the cluster, but there can be there are five nodes in our cluster. So whenever a broadcast message comes to a node, it will send an internal message of this corresponding format and saying that I have received a new value, so add this value in your state as well. So this is how we are going to solve this challenge. So as we saw earlier, the format for internal messages like this. So client usually sends message of this format, so type could be read or broadcast or topology. But whenever we want to send a message between node to node, we are going to print to the standard output a JSON of this format. So we are introducing a new type of the body of object of the body, which is internal message, and it contains only one field, which is a new message. And how we are going to process this message? So sending is, we understood how to send it. So it is going to, whenever it will be sent on every broadcast message, but this message, whenever this message comes to any of the node, we will identify it as an internal message. And if it is an internal message, we are going to add that corresponding new message in our state, which is the list of messages. So this is a simple solution for that. Now let's go to the implementation. So I've cleaned up my solution a little bit. The structure remains same. It is going to have a source and destination with a body which is of enum, which can be of any of the types that is provided by the client or the node. So initial message remains same, init OK response. Broadcast and broadcast OK remains the same. Read and read OK remains the same. Topology, we are not going to consider topology because in this solution I'm considering that each node sends to every other nodes. So you can also use topology. It may give a better result depending on the topology that is used, but since there were only 5 nodes, so it was not it was a bit irrelevant to also use the given topology. So this is the new field that we have added in this program. So what we do is internal message is going to send this field, which is a new message which is received on the broadcast. So overall implementation remains the same. This is the print and flash function, which is going to print to the standard output and flash its content. And so let me tell you how we have handled this. So messages is the hash set now, because we need to insert and extend it multiple times. So hash set is better, and they have also mentioned that the order of the messages does not matter, so it's always better to use a good data structure. And this node ID will consist the node ID of the current node. The cluster node will give us the names of all the other nodes in the cluster. So What I've done is initial message is handled as it is. We are just going to extract these two fields now because they are useful now. We need to know what is the current node ID and what are the other node IDs as well, because we are going to send messages to them. Initially it was not important because we were not performing any inter node communication. A read message, as it is going to send all the messages that we have. Broadcast message is now the same. It is going to insert the given message in our hash set list, and it is going to acknowledge it. And now we need to perform this, which is sending all the other nodes in an internal message. So we are going through all the nodes in the cluster. We are checking if it is not equals to the current node, because we don't want to send the same message to ourselves again and again. We are sending an internal message with the message that we received here. So broadcast message, the new message that we received, we are going to send it to the all the other nodes. So source in this case will be this node ID, which is the current node which we extracted from here, and destination will be all the other nodes which we are iterating here, and we are sending this message. I will discuss later how we are sending this message. Topology, we are ignoring it for now, we are not considering it, so I have not even initialized it here. We are just acknowledging it and moving forward. Internal message, so whenever a new message comes, we are going to insert it in our hash set as we saw earlier. So just one thing that I wanted to discuss is how we are sending the message. So for that, what I've created is I've created another thread which is going to send this internal messages. So if we perform this message inside this, so let's say here we wanted to send 5 messages. So until those 5 messages were delivered, the execution of this will be locked. So that is that will be a little bit bad on the performance. So what I've done is I'm going to ask another thread to send this message, because they are disjoint, it doesn't matter. So one thread prints to the standard output, one thread performs this reading from the standard input. So let's see how this thread is going to perform our sending. So this is our secondary thread which have spawned here, and this message sender and message receiver is the MPSC, multiple producer and single consumer channel, which is used to perform inter-thread communication. So this might be different based on your programming language, but in Rust we use a channel to send and receive data between two threads. So I have initialized two message sender and message receiver. This message sender is moved to the main thread because it is used here, and message receiver is moved to the secondary thread. So this move will pass the ownership from the main thread to this thread, and we are never going to use it. So that's why we are going to use this message receiver for receiving messages from this line. So this will send and this will receive. This whole operation performs in another thread, and this thread, what it does is it is going to receive the messages, and at once it is going to take 50 messages or less, at most 50, and it is going to print it immediately after that. So once it receives at most 50 messages, it is going to print it, and it is going to wait for some time. This is because we don't want to block the standard IO, because this print and plus function is also going to output to the standard output, and our this thread is also going to print to the standard output. So we need to make sure that these inter messages happen after certain intervals. They don't need to provide the immediate consistency that we saw in this diagram. So We don't need to say that these messages are sent immediately. We can wait for some time to send these messages. So these two messages, which are inter node messages, they don't need to happen immediately. We can wait and send them in batches. So that was how my implementation was, and based on these values you can get different results. So that is not of concern. Even if you send immediately, it will pass, the solution will pass, but I thought it was better to use some lag. Next up, this was the entire solution. So let me also go through what all we did, what all different we did in this. We introduced a new internal message, and we are sending it on every broadcast message, and every broadcast message is sending an internal message. This is the internal message that we are constructed, and we are sending it to every other node in the cluster. And for sending that, we are using concurrency. We are sending messages through channels to another thread, which is handler, which is going to take care of all the printing and waiting. That's it for the implementation part. Let me also go through the results. So as you can see, this will give you all the values for latencies, and so the maximum latency was 262. 99% of the time we had a max latency of 262. These values may be very less to even consider here. And we can also see one more thing here. So in the previous challenge, we saw that these server messages were all 0, right? Because we are not performing any messages. So but in this case we have sent some messages. So these are visible here. So if you go to the previous challenge, you can see that these values were 0. For client, they will always be present, obviously. Next up is the message diagram. So if you wanted to validate your solution, you can also see that. So in this case, we have 5 nodes, N0 to N4, and there were about 10 clients probably, and all of them will send some topology messages and this. So if you want to check whether your messages are going through, you need to check whether these messages are present, which is for the internal message body type that we introduced. So one more thing that I wanted to mention is this serialization thing. So this for this I'm using this SERDI crate, which is going to handle serialization and deserialization for us. And I've mentioned some things here. So this init OK is in camel case. So whenever serialization or deserialization is happening, we are going to consider them as a snake case operation. And this tag for type is also used to ensure that this is another field in this enum. So body will contain another field type with type and some value which is init or broadcast or read or internal message. So these are the features from SERDI crate. You can also go over them if you wanted to learn about Rust more. So this internal message, as you can see, whenever a broadcast message occurs, we are acknowledging it, right? We are first acknowledging it. We are acknowledging it first, and then we are sending 4 messages. We had 5 nodes in the cluster. Each node will send 4 other messages. So you can also see the chronology of these messages. So broadcast message comes, we insert it into our hash set. After that, we send a acknowledgement message, broadcast OK message, and then we start sending the what do we call internode messages, which is this for loop, right? and read will immediately return the read responses and so on. So whenever broadcast comes, these internal messages will happen, or they might happen at different intervals based on the values that we have used here, 50 or so. So it not might happen that all 50 messages are coming at in the message receiver at once, because at most 4 are coming. So this might be irrelevant, but it's fine. For later challenge we can use that. Yeah, so this is how you read these messages information. You can also go through. So a 12 comes as a broadcast, we are sending a 12 to every other node. So you can also see that this C1, so C10 client 10 sends N0 a broadcast message. This is how you read it. We are acknowledging it, and this N0 will send it to all the other nodes. So as you can see, it is not clearly visible here, but N4, N3, and these other ones are present here. So you can read this diagram to check whether your solution is working and all the messages are being propagated accurately. Yeah, so that's it for this challenge. I will make another description for the third one, which is fault tolerance. For the fault tolerance ones, there is only one condition, that they will introduce network partitions. So for some period of time, our these messages will not go through. So what the constraint that they introduced in this challenge is, this sender or send message will not go through for some period of time, let's say 2-3 seconds. After that they might go, but we need to handle that as well. So even if you print this, you don't expect that it has reached the other node. So we will look into that later. Thank you.